Welcome to a new video about analog filter design. In this example we will discuss the active bandstop filter having a Butterworth response characteristics. We will use the Geffe algorithm as we have done for the band pass filter realizations. There will be a fourth order band stop filter design, and we will see the circuit realization also, and we will verify these of course in the TI SPICE simulations after we have done the step-by-step calculations before that. So let's now look at our design example. The objective is to design a Butterworth response for an active band stop filter. The specifications are shown here. We need to have a maximum passband ripple of 2 dB. The minimum step band attenuation needs to be 15 dB. And the effective midband gain is 0 dB. So we have a unity gain at the midband part. The lower and upper passband frequencies are shown here. So 100 and 800 Hz. The lower and the upper stop band frequencies are 200 and 400 Hz. Okay, let's see what we need to do in our calculations. The first step is looking at the passband bandwidth, center frequency, and then from there the quality factor for the band stop filter. Okay, now the passband bandwidth is just the difference between the upper and the lower. That's given by this expression, and when you calculate that, you will have here 700 radians. 700 Hertz, or 2 pi times the 700 radians. So for 2 pi times this one is the 1400 pi radians per second. The center frequency is the geometric mean of the upper and the lower passband frequency. That can be also written like so, such that you have this in Hertz directly in the formula, and that will give you the value of 1777.2 radians per second. Now from there we can calculate now the band stop quality factor, which is the center frequency over the passband bandwidth. In this case that will be then 0.4041. Okay. Step 2 is looking at the normalized passband frequency, normalized stop band frequency of the prototype low pass filter. Because we always start with low pass filter prototype, and we will then transform that to the band stop filter. Now for that we use this formula for the normalized passband frequency, which is in most cases, and actually in all cases, 1 when you do normalization analysis. So we see here the omega bandwidth, or the passband bandwidth, over the difference, which is of course just 1. The actual calculation we need to do is actually this one, which is the normalized stop band frequency, and that is given by this formula, which gives us the 3.5. Now when you have now the values from here, we can calculate the filter order of the low pass filter, still the prototype. And for that we need to use the A max and A minimum. For A max we need to calculate then the epsilon p, which is a scalar value given by this formula, and it will give us now 0.7648. In a similar form for the epsilon s, using the A minimum of 15, that will give us now 5.5334. Now taking this all together in the formula of the filter order for the Butterworth response. And that's shown here. So you see again here the epsilon s, epsilon p, which is determined. Now that will result in 1.5797. Now we need to of course go to integer value, so we need to take the ns2. This is the order of the prototype low pass filter, not of the final design of the band stop filter. We need to also do the normalized Butterworth poles of the prototype low pass filter, and those are given by this formula, and of course written using the Euler's identity. You can also write like so. You see here the order n, which is in this case 2. You also see the k, which is the pole number. So we need to determine that. Now we have a second order filter prototype. That means we have one complex conjugate pole pairs, so we have 2 poles. Okay, these poles are given by this formula using this expression. You see already that we have to substitute 2 times 2, so that will be then just 4 here in the denominator for the cosine, also for the sine. Okay, the only thing we need to change is the k, so the k will be 1 and k will be 2, and that's shown here. So for k is 1 you get this expression, and for k is 2 you get this expression. And this can be then written like so, which is just work out the cosine and the sine, and you get also this one. This is actually, you can see that these are the complex pole pairs, which has the imaginary part here in the reverse sign here. So we have then P1 is equal to the P2 conjugate. So these are the 2 poles given in short form. Okay, now let's take this here and then move on with the next step. which is about the normalized cutoff frequency of the prototype low-pass filter. So this omega c, what we need to calculate, is required in order to transform our Butterworth poles to the required pole locations. Because the normalization required, since the poles are normalized here for the cutoff, and we actually look at the pass band. So the cutoff, normalized cutoff frequency is then calculated like so. We have the omega p, which is just 1. We have an epsilon p, which is determined, which was 0.7648. Now we also have our order, and we just substitute here, we get here 1.1435. Okay, the scaled Butterworth poles of the prototype low-pass filter. That's now the step we also need to carry out. Now we need to scale it up by this capital letter omega sub c. We have our poles, those are here, and we need to scale it up with this value. So we need to actually do this. So we take our poles, we multiply that by this value of 1.1435 we have determined in step 5. And that is just this. So approximately you get now this value. Okay, now we have our pole locations for the prototype low-pass filter, so the scaled. But since we know that we make a bandstop filter, we need to make the pole inversion. So we go to the high-pass filters first. So that is what we need to first do. Because we didn't do that by the bandpass filter, we actually did this and then went directly to the pole locations of the band pass filter. But since we go to the band stop filter, which is the inverse of the band pass filter, so we need to first also do the inverse of the prototype low pass filter poles. So that's actually what we have here. So we do pole inversion. Okay, now how do we do pole inversion? We actually look at the poles again for k is equal to 1 and k is equal to 2, and you actually look at your poles and you invert them. So you do actually 1 over what you have here, and that will result in this expression, and that can be then calculated using the complex conjugate in the numerator and denominator. You have these poles, and that will result in these two poles. So we have actually changed the poles from minus 0.8086 plus or minus j, again 0.8086, to these two poles. Okay. Now let's bring them together. And these are actually also the poles we will like to use in order to go to the band stop filter. So now the Geffe algorithm comes into play. We have now here the poles with sub g, which is our Geffe poles. The real part and the imaginary part of each pole will be then assigned to this pole of the Geffe, and which forms then the Geffe pole. And the Geffe pole is then given by this. We have here the real part, which is given by the capital letter sigma, and then an imaginary part given by the capital letter omega, as shown here. Index g, as said, refers to the stage number of the final band stop filter. Now we have two poles. We have here the two poles, but we need two stages times 2, which means we need to have 2 times 2, which means we have 4, or fourth order. So for each pole we create actually a second order filter. Bandstop filter stage 1, g is equal to 1, will then have this pole, which is this. You see here the capital letter sigma 1 has this value, also the capital letter sigma 2, which is for the other stage, but only changes now in the sigma 1 and the omega 1 and omega 2, because those are the inverse of each other. Step 9 is the Geffe parameters for each band stop filter stage. Now, since the poles of P1 had inverse and also the other one form a complex conjugate pole pair, we can calculate the Geffe parameters for both poles, and they will be equal to each other. Now the quality factor will be then exact same. The only difference is really the center frequency. So we will see that now. The bandstop filter stage 1, so g is equal to 1. That is first this one. This is the parameter for the Geffe algorithm. So we start now with the Geffe algorithm. C1 is equal to this. You substitute the value to get here 0.7648. Now we have here now the C1. We also need the D1. That's another parameter which requires the sigma, capital letter sigma 1, and also the quality factor we have determined for our band stop filter. You substitute here the value, you get here 3.0608. E1 is another parameter which requires C1 and also again the quality factor from the band stop filter. Now when you do the calculation, you get here 8.6843. Okay. The next one I mean is the G1, which is E1 squared minus the 4 times D1 squared. So you actually need those two. It will give you 6.1598. This Q1 is the quality factor of this band stop filter stage. So that is given by this expression. And when you calculate that, you get here 0.8901. K1 is calculated using this formula. So you just substitute the values we have and you get here 1.3622. W1 is related to K1 only, which is given by 2.2871. Now the center frequency of our band stop filter stage 1 is given by W1 times the center frequency we have calculated here in the beginning. And that will result here in 4065 approximately radians per second. Also a 0 which requires for our band stop filter stage, and that 0, which is for this first stage, omega Z1 is equal to omega center, which is then 1777.2 radians per second. This is now the band stop filter stage with the summary of the quality factor, the center frequency and the 0 frequency. Now we can move on and do the exact same procedure for the stage 2. But we know that the Q1 and the Q2, so the quality factor are the exact same, so we can take that. W2 is also equal to W1, so it's also exact same. The center frequency will be different. That is, the center frequency of the second stage will be the center frequency we have determined at the beginning, divided by now the W2. So it is not multiplied by, divided by. And that is now 777.03 radians per second. Now the 0 frequency is again the center frequency, so that is also 1777.2 radians per second. And now we have here the summary. So this is the band stop filter stage 1 and 2. Quality factors are equal to each other. Center frequencies are different. Why? Because the first one was omega center 1 was multiplied by this W1, and now we also divided that. So we have now two different center frequencies. The 0 frequency for each stage is the same, so which is equal to the center frequency here. Okay, now let's continue with this circuit realization. We have a band stop filter circuit realization which is developed by James Bainter. We will use that, which is then given by which has some features that we will use for our band stop filter. Now this filter, as said, is a second order filter, and which is actually shown here. So we see a lot of parameters. So we see in total 6 resistors, R1, R2, R3, R4, R5, and R6, 2 capacitors, and C1 and C2. And those are most of the time taking equal to each other. So C1 is equal to C2. So that makes the calculation also a bit easy. So that is what we also will do. Now there are 3 op-amps also. So we have here 3 op-amps. Okay, we need to cascade 2 second order band stop filter circuits to create a 4th order band stop filter. Okay, now we need to determine now the magnitude scaling factor and also the frequency scaling factor for each stage. Now, as said, we set C1 and equal to C2, which is defined as C. What we also do is we make this R5 and R6 equal to each other just for making the calculation a little bit easy. That's also defined as R. And we also define M1 that will then equal to the R1 is equal to R2, which is just a normalization. So this is 1, this is also 1, but they are equal to each other. Okay, the only thing left is actually the other parameters we also need to calculate. Now this circuit will result that the 0 frequency of each stage will be equal to the center frequency. That is the characteristic of this circuit. Because you can have a Butterworth response characteristics with different circuit realization, so it is not specifically this, but this circuit will do the job for our design. Okay, now the frequency scaling for each band filter stage will be equal to the center frequency. Now the magnitude scaling factor, Km for each band stop filter stage, can be calculated using this formula. So we see that is related to the capacitor for each stage. Okay, now the formulas for the denormalized components are shown here. R1 and R2, so the G is really the stage, so if you just skip that, you can see R1 is equal to R2 is equal to the Km, which is the magnitude scaling factor. R3 is our resistor here, which is given by this, which is again this M1, which is related to that R1 and R2. The magnitude scaling factor, and then also the quality factor here, which has also a parameter with the 0 and the center frequency for that specific stage, quantity squared. The next one is R4, calculated using this formula, and R5 or R6 were equal to each other. It was given by this formula. So you need these formulas for this specific circuit. So it can be different from the different circuits. Okay, the normalized component values for bandstop filter stage 1. And we select in this case C1 and C2 equal to each other. We give it a value of 100 nanofarads. And we know that our Q1 quality factor for the first stage was 0.8901. The frequency scaling factor was equal to the omega center of the first stage, so that's also what we have calculated. This is also what we already know. Now we can calculate the Km1, which is the magnitude scaling factor of the first stage. We know the C, we just determined, we just selected that. We also know this, which is then set to this omega center. So we have here 2460.3 is our magnitude scaling factor. Now the R1 of the first stage, so R1 of the first stage is equal to the R2 of the first stage, which is then equal to the Km of the first stage, which is then what we have determined here, which is now rounded off here. Now taking this here as K as the values for M is 1, we have our Km1, we also have our quality factors, so we can also use the zero frequency and also the center frequency. We end up here at the value of 7,230 ohms. The R4 of the first stage is given by this formula. You can also see that here. So you just substitute here the values, you get here 1,382 ohms. R5 and R6 for the first stage is given by this formula. Again, the quality factor and the magnitude scaling factor, you get here 4,380. Like we did for the first stage, we go for the second stage. We select now the C also equal to 100 nanofarads, so it means C1 and C2 for the second stage is also 100 nanofarads. The Q2 was equal to Q1, so that's also the same. The center frequency 2 for the second stage was equal to 777.03. That will be also the frequency scaling factor, so it will be different than the first stage. The magnitude scaling factor of the second stage is calculated using this formula, again similar to that one in general, so that will result in this value. We can move on as we did for the first stage, so going to these values for the R1 and R2, and R3 is this, and R4 and R5 and R6 are given by these values. So we have now all the component values for the first and the second stage for the bandstop filter circuit. The complete circuit is then given by this circuit given in the SPICE simulator. You see here the first stage and then connected to the second stage. And these were the values we just determined, the stage 1 and stage 2. You see here the 2460, that's here, 2460 again, that's here, so R1 and R2 for the first stage. We will now look at the simulation results based on the circuit we have just shown for our fourth order bandstop filter. This is the magnitude plot of the body plot. So you see here the lower passband frequency, because the baseline here, the gain, by the way, is the effective midband gain, is 0 dB, so that's also what we wanted. So the passband frequency, the passband region has a gain of 0 dB, so that's 1, so that is also achieved. You see at the 100 Hertz it is minus 2 dB, and it was also our lower passband frequency, and this is the ripple we wanted, so that's actually how much you want to go down. Looking at the upper passband frequency at 800 kilohertz, 800 Hertz, which is then minus 2 dB. You see also here the maximum attenuation. So at this frequency, which is our center frequency, we get now here a notch actually, so that is the lowest gain you have. Now, there is also a gain at 200 Hertz, so that is minus 19.48. This is the lower stop band frequency, and there we need to have a minimum stop band attenuation of 15 dB. We have minus 19.48, so we have at least 15, so that's fine. And also for the right side, the upper side, so for 400 Hertz, you see also the same value. For extra information, you see also the cutoff frequency. They are a little bit shifted. You see that because we are not designed for the cutoff frequency, but for the passband frequencies. And this is not a summary of the results here. You see also the center frequency again, which was calculated in our case as 1777.2 radians per second. And this value we have here from the simulator, we convert that to radians per second, which is now 1777.4 approximately, which is very close to what we have calculated. So we have achieved our goal here in our design. Right, this was our example considering the bandstop filter design having a Butterworth response. We have used the Geffe algorithm to create this filter circuit. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.